All right, can everyone see my screen?
Right.
Mhm.
Okay, great. So next we have Ian Hayes from University of Maryland, continuing on the theme of quantum criticality. Please, Ian, go ahead.
All right, thank you very much, Janelle, and thank you very much for the opportunity to speak here and share what I think are some pretty interesting results on specifically the magnetic field dependence of the Hall effect in this phosphoroscope system. First, I'll just give you a brief outline of the talk. I'll start with just a few words about what I mean by strange metal behavior.
Ian, I don't know whether it's me or whether others felt the same way. The voice didn't come across.
Yeah, maybe.
Can you hear me at all?
Yes, we
I
can
think
hear,
if you,
but it's
maybe
not
if you
clear.
get closer to the microphone, it might be.
Yeah, there's echo.
There's echo. How about if I'm here?
Yeah, much better. Yeah.
Is that much better?
Yeah.
Okay, I'll
Thank you.
hang out close to the camera.
Thank you.
Thank you. Yeah.
Okay. So yeah, the outline of my talk is I'll just start with a few words about strange metal behavior in high TCs, and then move on to this field dependence of the Hall effect in the phosphoroscope series. And to give you this sort of highlight, the field dependence is sort of going to give us a new way of characterizing where the strange metal behavior lives, and therefore what it's correlated with in the phase diagram. So in particular, it reveals a fairly clear critical fan in the temperature and doping phase space that suggests this behavior is linked to fluctuations of the ordered phase. And it's also going to show a very strong correlation with superconductivity, specifically in the zero temperature limit. So I'll show you those in due course. And then hopefully I'll have a few minutes to say what I think the broad implications are of this, of these results for strange metal physics and high TCs. And if you have further questions on this that I can't answer today, I'll just point you to the paper we just published on this exact subject just a few months ago. And of course, I need to start by thanking everyone who helped make this possible, including our previous speaker, Nicola, who helped a lot with these measurements, Professor James Annelides, and our fellow Berkeley student, Zayu Hao. And then, of course, the many people at the National High Magnetic Field Lab without whom we couldn't do these high field experiments, in particular, Ross McDonald, Arkady Schechter, Mun Chan, and Brad Ramshaw were very helpful in this. And this work's been supported by the Gordon and Betty Moore Foundation primarily. So to start with strange metal behavior in high TCs, people sometimes mean a lot of things by this. For my purposes, I'm just referring to the common set of transport properties that seem to characterize all these compounds, particularly near optimal doping. So the most famous example of this is the T-linear resistivity. And people will say this is strange for a variety of reasons. Either you can go to the low temperature limit, so it looks like you don't have quasi-particles, or maybe you cross the Monti-Alpha-Rega limit. For my purposes, I just care that the T-linear resistivity is this thing that is correlated with optimal TC in lots of cuprates and now lots of pnictides. So the T-linear resistivity is a famous piece of this, but there's also behavior in the Hall coefficient that is common to all these systems. So most cuprates show a strong temperature dependence, usually an enhancement, but sometimes it's a change in sign of the Hall coefficient that is strongest near optimal doping. And this isn't even limited to just high TC materials. Other unconventional or quantum critical superconductors show something like this. So cerium, cobalt, indium-5, I have an example over here on the left, shows a strong change in RH that is strongly associated with just the sort of critical region and highest TC. So this does seem to be a consistent feature of the superconducting state, or so I should say, superconducting materials in a broad class of compounds. Now, I probably don't have to introduce phosphorus dope barium 122 here, since we just heard a lot about it. But what I want to highlight here is that the observations we made previously about parallels between the field dependence and temperature dependence in the resistivity motivated us to look at the field dependence of the Hall coefficient and to ask whether there was some way in which the field dependence there gives us another way of characterizing the strange metal behavior, what it's correlated with and where it might be coming from. So that's really the motivation for the data that I'm gonna show you now. So start with optimal doping. This is the Hall coefficient at low fields for optimally doped barium-122, 31% phosphorus substituted. And I should start by saying that for all the data I will show you, the field current configuration is that current is passed in the field, in particular along the A-axis, and field was applied along the C-axis. That'll be the same configuration for all this data. Now, looking at the temperature dependence here, there's temperature dependence all the way up to 300 Kelvin, but especially at low temperatures, you start to see a sharp upturn that is reminiscent of what I just showed you in the cuprates and in some heavy fermion compounds. And so the question we'd like to ask, is there any distinctive field dependence in that region? So if you go to the middle of that upturn, somewhere around 75 Kelvin, and measure Rxy, the off-diagonal resistance as a function of field, you'll see that it's actually sublinear. So if you were to define an effective Hall coefficient at each field, that's Rxy over H, say, then you would actually see it's decreasing with field, qualitatively similar to what happens when you increase temperature. And furthermore, this only happens within this low temperature upturn region. So if you go up to 200 Kelvin, you get a very straight Rxy all the way up to 60 Kelvin. So this has the makings of an interesting correlation between a particular field dependence, a decreasing RH with field, and the strange metal property or the strange metal behavior in the temperature dependence, increase as you go toward lower temperatures. And I will show you, based on where this particular field dependence lives in the phase diagram, that it's very unlikely to be a simple band structure effect. Probably is related to whatever scattering, whatever interactions are responsible for superconductivity. But as was mentioned many times in the previous discussion, barium-122 is a multi-band system, and so you can get both temperature changes in RH with temperature and changes in RH with field in very simple multi-band physics. So I just want to say a few words now about what one expects for a system like barium-122 based on the simplest multi-band model. So if you have multiple bands, the sort of simplest thing to do is add the conductivities in parallel, and it's a Ashcroft-Mermin level problem to just put them together. And there are just two limits I'd like to highlight for you. One is the H equals 0 limit. In the H equals 0 limit, you get a Hall coefficient that's just the weighted average of the Hall coefficients on the different surfaces, weighted by the conductivities in the respective surfaces. And then there's the high field limit, in which you get an effective RH that is determined by the total carrier number, electrons minus holes. And so generically, in a system like barium-122 that has electrons and holes in approximately equal numbers, you'll start from a fairly small RH, because these two terms will nearly cancel. You'll go to a very large RH as your N total, electrons minus holes, goes towards 0. So the generic thing you'd expect for this system is for RH to start out small and get large. If you were to have two carriers of the same type, then you'd expect the opposite behavior. It starts out high and then gets smaller. And because barium-122 has 4 bands, this is a possibility, but there's quite a bit known about the band structure of barium-122. And in particular, in the phosphorus dope series, there's actually quantum oscillations that give us some idea about what the relative mobilities are on those two electron-like sheets, which dominate the Hall coefficient. And they are close to equal. They're, within 50% or maybe 100%. And so that allows us to do just basic simulations and ask how much field dependence should we expect from that? And the answer is not very much. You still expect the hole and electron balance to dominate and for the Hall coefficient to simply increase with field. You would need a sort of unrealistically large difference between the mobilities on the two electron sheets to get a low field decay in the Hall coefficient. And even then, it's not going to be very large. So this can't rule out multiband effects as the origin. There's a lot of effects one could layer on top of each other to get very complicated behaviors in the Hall coefficient, but it's at least not the natural thing in the first order calculation that you would do. And as I'll show you, what I'm calling the strange metal field dependence, where RH decreases with field, is confined only to very special parts of the phase diagram. All right, so back to data. I just want to show you more generically what RH looks like. So in the rest of the talk, I'll just plot RH, which I'm defining here to be R rho xy over the field, because that's what gives you it's what makes it easiest to see the field dependence. And so generically, what you see throughout the phase diagram is some region of decreasing RH, which flattens out, the field dependence decays, and eventually you get an upturn, an increase in RH at high enough field. Since that's what we expect from multiband physics, that's naively what we'll attribute it to. And in fact, you'll see eventually when you get to the far overdose side of the phase diagram, pure H squared is in fact what you see. Other than that H squared, the curve is sort of generic. And so what I'm going to show you next is basically how much you can decrease RH by applying a large field throughout the phase diagram. If you want more details on how we do this, I'll point you just to the paper we published, or we can talk about it later. I don't want to spend too much time on it because all of the important correlations that I want to talk about are readily seen in the raw data. But just to focus on, just to give you a basis for what I'm going to show you in the next slide, throughout the phase diagram, we try to estimate how much can you actually decrease RH by applying a large field. So when you do that, this is what you get. This is an intensity plot for that strange metal field dependence in the doping and temperature plane. And I've started here at 30%. I've neglected the underdoped part because the transition to the antiferromagnetic phase involves reconstruction, as we heard in the last talk. And that radically changes the Hall coefficient and gives you different field dependence. So to compare apples to apples, we're going to stay on the disordered side. And there are two things I really want to draw your attention to about this phase diagram. The first is that if you look at high temperatures, the strange metal part of the Hall effect is independent of doping. Throughout the very broad region of doping space, you simply get the same field dependence for all your samples. As you decrease the temperature, the window over which that is true decreases. And it decreases continuously and seems to vanish near 30%. And thereby traces out the kind of fan region that you would often draw when describing quantum critical systems with a single tuning parameter. So this looks very much like there's some detuning energy in the system that is getting stronger as we move towards higher phosphorus doping, such that if temperature is larger than that detuning energy, you simply get the same effect, independent of what your actual doping value is. So this is striking. There aren't too many things in too many experimental observations that actually paint the fan in quite this clearly. So this is fairly striking evidence in favor of the idea that this effect is coming from the influence of the nearby ordered phase. The second thing I want to draw your attention to is what happens at low temperatures. So when you cross that fan-like region, the strange metal field dependence weakens, and it continues to weaken, but it doesn't weaken all the way to zero at zero temperature. There's an extended range over which you still see a decreasing RH with increasing field, and it's strongest near optimal doping, and it decreases for higher phosphorus content, and then vanishes at the same point that superconductivity vanishes. So if you go just beyond the superconducting dome at low temperatures, you see none of this decreasing RH with field, you see pure H squared. You can recover the decreasing RH with field if you go to higher temperature, but specifically the low temperature part of the Hall coefficient seems to be strongly correlated with superconductivity.
Ian, do you mind if I interrupt you?
Yeah, not at all.
If I take the dashed line literally, it's somehow in deviation with my understanding of what happens in the phosphorus doped materials. In other words, the scale doesn't, the critical slowing down doesn't actually go all the way to 0, that even at around optimal doping, there seems to be various indications that there's some truncation. So the dashed line, in that sense, I would have thought that, you know, it doesn't really terminate to 0.
That could well be true. So it's a little difficult for me to answer with the high fields data because of the very limited field range available at optimal doping. So I'll show you the raw data in just a little bit. When I do the fits and try to estimate how large the strange metal RH actually is, it does top out at around 10 to 15 Kelvin or something.
Okay.
So that is potentially consistent with that. If you have some cutoff of about a few Kelvin in this sample. The other thing I'll point out is that the antiferromagnetic phase actually ends at 28%. So I'm a bit off the exact critical points, you might say. And that was chosen to just make sure we avoid any accidentally entering the antiferromagnetic phase.
Fair enough.
Your observation is fair, and this is really just a guide to the eye determined by the data points that I have. And there's only so much I can say down here. But it may well be consistent with a small cutoff. So let me start by showing you what the data looks like at low temperatures. So these are just slightly overdoped samples, 36 and 45% phosphorus doping, so they live around here. You can see a strong decrease in RH at moderate temperatures of 25 Kelvin or so. And then that decrease definitely weakens as you go to lower temperatures. At higher fields, you can see that the increasing RH is setting in again. And in between there, there's sort of a balance between the two. So you can see it's a little bit stronger for the 36%, whereas at 50 Kelvin, you're already moving into the H squared regime for the 45% doped. In each case, there is still a bit of decrease that you can observe. And if you continue all the way to the overdoped, the very edge of the superconducting dome, at like 73% phosphorus substitution, this is a sample with an about 1 Kelvin TC, it's right on the edge. You see a very small, 2% or so decrease in RH at a few Kelvin. And then if you go to the next sample over, you don't see any decrease at all at 2 Kelvin. What you see is a pure H squared fit, which seems, well described by simple multiband. So you can see directly by eye that whatever this decreasing RH is at low temperatures, it vanishes at the same time as superconductivity. Now, the second thing I'd like to show you in detail in the data is what the fan looks like at higher temperatures. So if you go to very high temperatures, what I've plotted here is RH minus RH of 0. So this is just the field-dependent part of RH, which I do to compare samples from different parts of the phase diagram that have fairly different background RHs. Now I just want to back this for a second and point out that this is what you expect to happen just from multiband physics. The conductivities on all these sheets are getting better as you go toward the overdoped side, and so you expected this term to get smaller and smaller as this in fact does. But if you just compare the field-dependent part, and just look at this decrease of RH with field, that part is exactly the same at high temperature. It's fairly small, but it's resolvable, and the curves lie right on top of each other. If you go to lower temperatures, there's still a region in which curves lie on top of each other, but the most overdoped samples start to show a weaker field dependence. And if you go to lower temperatures still, that trend continues, with the intermediate dopings showing a slightly weaker field dependence, and the common field dependence existing only over a doping near optimum. So once you just plot the field dependent part of the Hall coefficient, it becomes relatively easy to see that there is a constant thing whose constancy is shrinking as you decrease temperature. And you can see this in the temperature dependence of the Hall effect as well, but it's a little trickier because of the background. This is one thing I really want to highlight about this use of the field dependence to characterize the strange metal behavior, is that it allows you to make sort of cleaner determinations about which part of the Hall coefficient is actually correlated with superconductivity and with proximity to the antiferromagnetic phase. If you look at the temperature-dependent part, there's some slight temperature dependence at high temperatures. You see the upturn, this is the data you saw before, that can be suppressed with a large magnetic field. And if you go to the overdoped side, you still see the upturn, but it ceases growing at sort of successively higher temperatures, so that by the time you're on the overdoped side, it still looks relatively flat. And it would be fairly hard to characterize this background well enough to measure this without the field. So just to quickly recap those observations, by looking at the field dependence of RH, we're able to tease out a certain part of the Hall coefficient that seems to be correlated both with superconductivity and with proximity to the antiferromagnetic phase. It allows us to trace out actually a nice quantum critical fan. Now, in the time that I have left, I want to say just a few words about how this relates to other materials and what it might suggest about the broader picture of strange metal behavior in high TC. So first, I want to acknowledge that there's some recent nice work actually coming from Nigel's group on the field dependence of RH in thallium cuprates. And there are some qualitative consistencies here where the Hall coefficient decreases with field, and that weakens as you go to lower temperatures on the overdose side. I'll leave it to you to read that paper and determine how similar you think they are. But I think it's a very interesting point of comparison and suggests that something about this may be universal to all these high TC materials. The second comment I want to make is that it's rather striking that this strange metal field dependence seems to come in as an additive term. In other words, the absolute value of the change in RH is the same as a function of field at high temperature across a range of doping, despite the fact that the zero field RH is changing quite a bit. And so if we think that this effect is coming from some change in mobilities or carrier densities, even something generated by an unusual anisotropic scattering rate or antiferromagnetic fluctuation, you still think that the effect would then be filtered through this multiband formula and the competition between the Hall coefficients on these 4 different Fermi surface sheets, which are all changing across the phase diagram. The fact that it gives just one field dependence makes it look a lot like it's coming in some more direct way, which is an interesting issue that's going to have to be explored further. And naively, it seems fairly difficult to figure out how to get that behavior. Then the next thing I want to point out is that this sort of extended range of critical behavior at low temperatures actually draws barium-122 into closer parallel with a number of cuprates which show some sort of extended critical behavior on the overdoped side. So there are a number of materials that show T-linear resistivity at low temperatures. LSCO has been shown to do so through high field measurements. Electron-doped cuprates, where you can measure the low temperature resistance fairly directly, also show a T-linear behavior that vanishes near the overdoped side. And those same films also show a logarithmic upturn at low temperatures that diminishes, that's often characteristic of quantum critical systems, that diminishes and vanishes at the same point where superconductivity does at the overdoped side. And this is nicely laid out in a paper by Nigel that contrasts the way criticality seems to emerge in pnictides and cuprates, whereas in the cuprates, you seem to have an extended region of some sort of critical behavior going up to the edge of the superconducting dome. The pnictides up until now have seemed more conventional critical systems in the sense that things are concentrated really near a point where the antiferromagnetic order ends. I think one takeaway of this observation is that there is more of a connection between these 2 scenarios than originally may have originally seemed to be. So you can see pretty clearly there's some region where it looks like temperature is exceeding some detuning energy and you're getting uniform behavior. And you can cross below that, but that doesn't result in a continuous decrease of the effect down to 0 at 0 temperature. the effect sustains itself for all superconducting samples. And so it almost makes it seem like in the nuclides, you can see two energy scales. You can see the main detuning energy, which gives you this fan-like region and some region of doping independence in the Hall response. Then there's some other energy or time scale that makes those fluctuations or the effect of those fluctuations in the transport non-zero all the way down to zero temperature. There's something that sustains the effect throughout this region. So that'll be an important avenue to consider in the future. The final thing I'd like to say about these results is that they provide potentially more information about the structure of the interaction that is responsible for superconductivity. So there's been a lot of work correlating the T-linear term in the resistivity with Tc, and that's been seen in a lot of materials, cuprates as well as pnictides. And the analogy being that the stronger the scattering is, the stronger the interaction is, and therefore the stronger the attractive part of the interaction will be. The resistivity by itself doesn't allow you to factor out which part of the interaction, it doesn't give you any information about what part of the interaction is going to be attractive ultimately at low temperatures. Whereas in the Hall coefficient here, we see a temperature evolution of the behavior. We see some zero temperature part where the correction of the Hall coefficient seems to be exactly related to whatever attractive part of the interaction there is. And then you see some thermal evolution such that even non-superconducting samples can exhibit this behavior on the overdose side. So there's quite likely even more information present in the temperature dependent of the Hall coefficient here, once you've been able to factor out everything with the field. All right, so with those admittedly very broad statements about what I think the implications of these results are, I just want to remind you of the highlights. By looking at the field dependence of RH, you can isolate a fraction of the Hall coefficient that seems to correlate both with superconductivity and to exhibit this intriguing fan-like feature that seems to tie it to the behavior of the antiferromagnetic phase. And if you have further questions, I direct you to the paper we just published, or you can ask them right now. So thank you very much for your attention.
Thank you very much, Ian, for this talk. Any questions, comments? Let's start off from Nigel, please.
Thanks, Ian. A very clear presentation. It's beautiful data again. And I guess I wanted to link back to Nicola's talk, where it shows, very striking agreements between, the phenomenological magnetoresistance, the measurements, and the theory of Koshelev based on Spot's picture, also around 31%. And so I was wondering, what are the specific predictions for the Hall resistivity within that model, and whether they show any relation to the data that you present?
So I think qualitatively can produce an enhancement of the Hall coefficient with anisotropic scattering generically. It has this sort of similar effect to having two sheets.
Yeah, but specifically the field dependence. Yeah.
Oh, specifically the field dependence. I think generically you do expect whatever increase in RH you get from anisotropic scattering to decrease with field. So that way it is actually consistent. What I would like to see, and haven't seen because I'm sure it's difficult in a system like this, is whether you can actually reproduce a consistent field dependence at high temperatures despite all these changing background conditions. It's probably not impossible. The question is whether you're just going to be tuning parameters at the end to make it fit.
Yeah, but it seems very, your data suggesting a very systematic behavior, which sort of almost independent model, which is kind of, of course, we've been measuring magnetoresistance and Hall effect, and we really struggle to fit the two side by side in any kind of Boltzmann type picture. I guess I think what you're saying is it's probably the same here too.
Yeah, I think, next to each other is fairly hard. So it may well be that a lot of the magnetoresistance is coming from heat of the Fermi surface. And then there's some extra ingredient that shows up in the Hall coefficient that is just separate from the Fermi surface. It sits on top of it.
Interesting.
It's unclear how they're related.
Thank you.
Any other questions, comments? Maybe I can ask sort of a question following the lead you were giving towards the end of your talk, connecting different materials. So the Hall coefficient in like heavy fermion quantum criticality going to vanadium doped chromium, etc. They seem to have very contrasting behavior, and there are various ways of analyzing it. But one way that has been fruitful in those two type of systems for comparison is to look for the isothermal dependence of the Hall coefficient and see whether, first of all, there's any rapid change in the vicinity of the quantum critical point, and if so, whether there's a sharpening as a function of temperature. And so in chromium systems, that the answer is no, there's not a huge change. And in any case, there's not a lot of sharpening. And in some of the heavy fermion quantum critical systems, the answer is yes, there's a very sharp change, and there's a very strong, very sharp crossover features, and that crossover feature sharpens as the temperature is lowered. And so you have this extensive, impressive collection of data in this system. And I was wondering whether something along that line could be looked at.
Yeah, so a question of how quick the transition is between, say, the totally normal Hall coefficient on the overdoped side and the optimally doped or underdoped behavior.
Yeah, because you say, you refer to the strange metal component of the Hall, and one could perhaps look at that.
Yeah, it's a good question. Looking at it in detail will be a little tricky because of the limits of high field measurement. Broadly, as a function of temperature, it sharpens a bit. So just looking at the color plot here, you can tell that there's a broader region of enhancement at intermediate temperatures, and it kind of sharpens up as you go towards lower temperatures. Can you describe what accounts for that difference between vanadium doped chromium and the heavy fermion material?
Yeah, it's tied up with the very drastic Fermi surface change on the two sides of the quantum critical point that happens in heavy fermion system that doesn't happen in the more sort of conventional spin density wave quantum critical point.
Yeah. Yeah, to me, what's most striking here is that it doesn't seem to sharpen up totally, that no matter how low you go in temperature, there's some finite width here, which seems to characterize the superconducting dome.
Which might be related to the truncation of the quantum criticality on the temperature axis.
Okay. Is there something quantitative to look for in terms of the width of that behavior and maybe the truncation along?
In terbium rhodium to silicon to its linear in temperature for 1.5 decades of temperature.
Okay, well that is a good suggestion.
Yeah, thank you. This is certainly a large body of data that you collected and looks really interesting. Any other questions, comments? If not, let's thank both Ian and Nicola for a really good combination for this fascinating story, evolving story. Thank you.
Thank you very much.
Very nice talk. Thank you.
Thank you.
Thank you. Bye.
Bye.
Bye, Jimmy. Bye, everyone.
Good to see you, Hilbert.